Pod? Did we finish it Friday? I don't know if we did or not. No, I don't think we did. And if we need to, we will come back to it at the end of class. I want to get through 2.3 and 2.4 first because it's morning. It's just on speed and velocity, which the Nearpods we have scheduled for tomorrow are also on speed and velocity. So we'll be good if we don't really come back to that just yet. All right, so let's see. Physics. Nope, not National Honor Society. I need physics. Come on. Physics. PowerPoint. Did you check in through the office? Okay. Because I'd already done attendance. All right, so we've already done. Come on. You're having issues this morning. Oh, we're not in chapter 1. What am I doing? We're done with chapter 1. Sorry, we're in chapter 2. So y'all, 21-0, huh? 21-0? Was that the score this weekend? Friday. Against Brewer, it was 70-0. No way. Wow.
And what's worse is
what happened?
they just
I kept messing up.
Well, obviously.
But what's funny is that they got on like Facebook, I guess, and like the parents of Brewer was like, oh, you should have given 70-0. You should have given us like a mercy rule or something. And then
Well,
we were like,
well.
we did. We put a dirt string
Oh,
offensive line. And
Oh gosh, and it was still 70-0.
Is
Is it always that they just having a bad year? Is it always?
I think 4 years ago they were good,
Yeah.
but now they're not good. Yeah, they took the first string offense and defense out on the second half.
Wow.
Third quarter, it was second string, and then they put their third string, and we're like, we're still scoring. And stop.
Wow. Wow. Okay, here we go. Position versus time graphs. That's what we're going to talk about today. Position versus time graph is any graph is just an alternative way of having a data table. So you make data tables, and you can see some trends with that. But when you put it in the form of a graph, it really helps you to see that trend a lot better. So one position on a position versus time graph, we're going to plot the y-axis, and the x-axis is going to be time. So you might want to write that down, because like any x-y axis, we have the independent variable is going to be on the x-axis, and the dependent variable is going to be on the y-axis. Well, time is always the independent variable. Time is always the thing that we're going to choose, our time intervals, or we're going to choose how long we're going to let this go or whatever. So time is always going to be on the x-axis. And that's going to make your life a whole lot easier, because then whatever else you're measuring is going to go on the y-axis. It's going to be your dependent variable. So make sure that you write that down. Time is always plotted on the x-axis because it's always the independent variable. When we're doing position versus time, we're doing distance or displacement versus time. So that means that the position is always going to be on the y-axis, and the time is always going to be on the x-axis. Okay? Okay? All right. Come on now. Not sure why I have two of these, but I do. So here's some examples. So here's our data table. We're plotting something or we're timing something for 5 seconds. And here is how its position changes in that 5-second time interval. Here's the graph. Now, please remember when we're doing actual data, like when we go out Friday, hopefully we'll go out Friday and we'll do our run for it lab. We'll do our speed versus position lab. So dress appropriately. You're not going to get nice, even points like this that's going to make this nice, beautiful, straight line graph. You have to do a line of best fit. Okay, remember that means you're going to have some dots, some points all over the place. You might have some here and here and here and maybe one way over there and then one here and here. So we figure out where in the middle of all those dots is going to be the best place. And that's our line of best fit. Where is it going to hit the most, or where is it going to be kind of the average of all of those? That's our line of best fit. Which is a little, okay, obviously this one doesn't work. There we go. So a line of best fit drawn through the data points can be used to learn additional information about the object's motion. So here's the important part. To find position at a time not in the original data, actually, hold on a second. All right. Yeah, you can write this down, but you probably know this already. So let's say we have a time that's not actually a time that we measured. Let's say I want to know what the time was at 2.5 seconds, or what the position is at 2.5 seconds, and I didn't necessarily measure 2.5 seconds. We're going to interpolate. Interpolate means I look at the graph, I find the time, I go up till I hit the line, and then I go across. And that's going to give me my position. So my position is approximately 1.25 meters. That's interpolation. Extrapolation would be if I did it on out past the graph, like you see right here. So our graph time stopped at 5 seconds. But if we want to know what it is at 6 seconds, we go over to 6. We go up to where we would hit the line. If we continued the line on out, where we would hit it, and then we go across. So our position would be 3 meters. That's extrapolation, because you're going beyond the graph. Interpolation is when you look within the graph. Okay. So you're going to have to learn how to do that with those graphs. So a lot of times I'll give you a graph and I'll ask you, all right, if you're at time here, what's your displacement? Or if you have this displacement, what's your time? Or if you were to go to this distance, predict what the time would be. And that's where we would use that extrapolation, okay? And you can just use the graph to get that information. All right, now, remember back to algebra, what is slope equal to? Rise over run. All right, well, yeah, but what's rise? The change in y, right? And what's x? What's run? The change in x, okay? So your slope, and that's why we always wrote it delta y over delta x. That means the change in y over the change in x. And slope is really what we want to do, the information we want to get from these graphs. The interpolation, the extrapolation, all that's good. But we want to look at what slope can provide us. So make sure you know how to find the slope of the line. Okay? Change in y over change in x. And you can use any 2 points to calculate the slope of the line. So on an object position versus time graph, the rise corresponds to the position and the run corresponds to the time, which that's just, like I said, change in x over change in y. So there's nothing really new on this particular slide that you'll need to write down, as long as you know how to find slope. which I'm going to assume at this stage in your life, you do. But if you don't, it's change in y over change in x. And this is just showing you an example of that, okay? They did the old counting on the graph thing, where you count the blocks over and you count the blocks up, and that's fine. What might be a more accurate way is to use 2 points from the data table and actually subtract those 2 points to get your change in y and your change in x. Okay, so let's look at some of the information we can gain by looking at a graph, because if we look at this graph, it is not a straight line graph, right? It's kind of this weird, funky looking graph. And so we need to know, what does this thing mean? If I can find the slope of the line or not find the slope of the line, what does that mean in our situation? So a straight line position versus time graph can have a positive slope, a negative slope, or a zero slope. This you will want to jot down in your notes. A positive slope means a positive velocity, means you are increasing your speed in that forward direction. Okay? So a positive slope means a positive velocity. Now remember, I said velocity, right? Not speed necessarily. I said velocity. Or if I did say speed in the forward direction. Remember, that's velocity. Okay? So the positive sign there means that it's not just the speed, it's speed and direction. Okay? And negative slope would mean a negative velocity. Well, what would a negative velocity possibly mean? You're slowing down, or you're going in the opposite direction. You're going in the opposite direction. Okay? So what would a zero slope would mean? You would have zero velocity. Well, what does that mean?
The same position.
Not same position. Well, okay. But what would that mean as far as if you're out running or you're riding your bike or something like that and you have a zero velocity?
Same rate.
Yeah, you're going the same speed. You're not increasing, you're not decreasing. Okay, you're not going faster, you're not slowing down. You're carrying that same velocity the whole time. Okay? So like this portion of this graph would mean if we're out riding a bike, okay, then you are speeding up. You're getting faster and faster and faster at each time interval. Here, at each time interval, you're slowing down. Okay? Here, you're just going a nice, steady, even pace, same pace the whole time for that whole interval. Okay?
I'm sorry. I guess I look perplexed because you're at the same position.
Yeah, the position stays the same, but the time keeps moving. So you'd be stopped on the
Yeah,
flat part,
that's what I thought.
and then the negative part.
You might be right. You're right.
backwards.
I know I'm getting my velocity and my acceleration mixed up. Sorry about that. That's a different graph. So yes,
There's a problem like that.
Yeah. you'd be stopped. Yeah. I was skipping ahead. Sorry. Okay, let's look at the next slide. I'm probably getting ahead of myself in here too. There we go. The greater slope means a greater velocity. So greater slope means greater velocity. And instantaneous velocity, we talked about that a little bit. And we said it's the velocity at a particular second or a particular instant in time. And the way we find that is we find the slope of a tangent line. Have y'all ever done tangent lines before? Okay, so then you know what that is. So instantaneous velocity would be this, you would find it by doing the slope of a tangent line on a position versus time graph. Okay, so it's at one particular little instant. It's the change in distance over change in time.
Is it bad if we don't remember the tangent line thing?
Oh, okay. No, it's not bad. So let's say tangent lines are usually on things that are not a straight line, obviously. So let's say this is our position versus time graph. And here you are at time 5 seconds. And you want to know the instantaneous velocity at time 5 seconds. Well, that's not a straight line. How in the world are you going to find slope? How are you going to do this? You draw a tangent line. So you draw a line that just touches at 5 seconds, a straight line that just touches at 5 seconds. You find the slope of that straight line. So you're going to find the slope of this straight line.
Does it go all the way up, or does it just do it?
Well, you're only going to look at that one little point. It's got to touch that one point on the curve.
Does it matter if it's like this or like this? It just has to be a straight line?
It has to touch that particular curve. Yeah. There'll be a little more. We won't have any that are terribly confusing, I don't think. But for right now, we'll get into some of those a little bit later. But tangent line is a line that just touches one point on your curve graph. Yes.
There was a question in the book where you had like 3 lines that look like that, and they're sectioned off to A, B, C.
Mhm.
You wanted the average velocity.
I was
So,
confused on that.
so in order to find the average velocity, do I just find the slope of 3 lines and then add it up and then divide by 3?
Just off of what you're saying without reading anything else, I would say yes.
Okay.
Yeah. All right. So position versus time equation of motion gives the object's position at any time if its initial position and constant velocity are known. So your position versus time equation is given right here. This will be another equation that you're going to want to memorize and have kind of in your bank of equations. So the final position of an object is equal to its where it started plus its velocity times its time. So, and if you think about that logically, that equation should make sense to you. If I start here and I end at the band room, then I need to know how fast I'm going and how long I'm going that fast is going to determine where I'm going to end up. Okay? So if I'm going to run at 11 and a half miles per hour, no, not 11, that's minutes per, my pace would be 11 and a half minute mile. So what would that be? 5.5 miles an hour. If I run at 5.5 miles an hour for 1 hour, how far am I going to go? 5.5 miles. So I'm going to be at starting point 0, and I should be 5.5 miles. I should end up 5.5 miles down the road, assuming that my velocity is the same and I travel for an hour. Right? Does that make that equation should kind of be a logical how we got to that equation. Oh no. Clear screen. Well, now that square is going to be stuck there forever. But that's okay. All right, so there's an example of our position versus time graph. So here's our initial position. Our final position is going to depend on how long we move and how fast we move. So what other equation does this look like in math? Just a linear equation. I'll put it in my box. Y equals mx plus b, right? Okay. So y would be like my final position. B would be my initial position. M would be my slope, which would go to velocity here. And the x would be my time. Okay. So it looks very similar to a straight line graph, which is what we have, a straight line graph. So the slope of this is going to be our velocity. Okay? Oops. Now the straight line is going to be on there forever. Forgot to pay attention to that? Well, you're going to learn it now. All right. So here's an example. A skateboarder with initial position of 1.5 meters moves at a constant velocity of 3 meters per second. What is the final position of the skateboarder? Okay, so let's look at our equation. What equation are we going to use? The position equation. X final equals X initial plus VT. Okay, we know what is the position of, okay, so here it is. Substituting 1.5 meters for the initial position and 3.0 meters per second for the velocity, and then we plug in the time, which unfortunately they did not tell you what it was in that example problem, but in your homework problems they should tell you 2.5 seconds, because otherwise you can't figure this out. So you'll put in your velocity, you'll put in your time, you'll put in your initial position, and then it's just plug and chug. No big deal. Okay. And there we're just relating the position time equation to the slope of a straight line. And all we did, or the equation of a straight line, all we did is we switched these two terms, which, since we're adding them together, it doesn't matter what order we add them in. This is I wish it wasn't messed up, but this is a really good graphic to help you see the relationship between the straight line graph and the position versus time graph. So you might want to jot that down. Or I'll rewrite this one since it's a little hard to see. Okay, so remember M is going to be the slope of the straight line. In the position versus time graph, our slope is V. X and T are both the horizontal axis. Y and XF are both your vertical axis. The y-intercept is the place where it crosses the x-axis, or when x is 0. And for us, the initial value or the initial position is going to be where time is 0, where y is 0. X is 0, sorry, where x is 0. Ooh, it's a Monday. So I would write both of these equations down and then just have, like they have listed out what each of those parts are equal to, what they both represent, so you can see they're essentially the same equation. And there will be lots of equations in physics that are just derivatives of the straight line equation, depending on what we're graphing. Okay, we got that down, everybody? Okay. Okay, so this may be in like some of the ones y'all had on a homework equation or homework problem. We have two lines on the same graph. We have line A here, and then line B. So this is line A. This is line B. And what kind of information can we get by looking at two lines on the same graph? Where they intersect is where they have the same location. So that's what you need to know. Where they intersect is where the objects will have the same position. Okay? It's kind of like when you solve two systems of equations in algebra. And so you had two equations and you had to solve x and y for both of them. A lot of times if you graph them, where they cross is where the two equations were equal to each other. So same kind of thing here. Where they cross is where they have the same position. And that should be, I guess that is the end. Yes. Okay. So, with that in mind, do we have any questions about homework problems from 1 through 25 or from tonight's homework will be 26 through 39? Anything on 1 through?
I don't think we did one.
We not do one today.
Okay. We just did 26 through 39.
Oh. Well,
But I did
okay. Well, so y'all have already done 26 through 39?
Yes.
Okay, well then let's switch that up. Let's just switch that up and tonight do 1 through 25. They'll be like super, super easy. Because y'all did the hard ones first.
For real?
For real.
I thought I just didn't know how to do it.
No.
Me too. I was like,
I will go over any questions you have on those sections. But tonight's homework, let's change that up and do 1 through 25 for tonight. Okay? So 26 through 39, questions.
I think they're up to 40 of them, right?
Can you just go through a bunch of them? They were all kind of.
Can I use the bathroom real quick?
Yes and yes.
Okay, I have a specific question. Not even
Okay.
on a problem, just like a general one.
Okay.
So a lot of the positions were like negative, and
Uh-huh.
so when you would try to do like the X, you know, the initial or the final minus the initial, like I was like, okay, so 2 negative, X is positive, and then I was adding the number, and I was like,
2 negatives make a positive only when you are multiplying.
no,
Oh.
like 5 minus -3. So it'd be like
Final
E
minus
change.
initial.
Oh, yeah. It's always final minus initial.
But if the initial was negative, it would turn into a positive.
So like on number.
So you would just put it in -5 minus a -3. That is going to equal -2.
No,
right?
the 5 was positive, so it was like 5
Okay,
minus.
5 minus -3. So that would be 8.
Okay,
yeah.
I didn't know if like math rules applied. Like
They
that.
apply.
Because it was like 1 and 7, 1 and 1/7, and I was like, that doesn't look right. And I was like,
No, that's fine. No, that applies. That's fine.
Oh my god. Duh. That math rule doesn't apply. Just,
All math rules always apply.
well, not making them into complex fractions when it's meters per second.
Well, yeah. Okay. You can just give me a decimal answer. It'll be fine. All right. So number 26.
And how do you do negative meters per second? Like, you go backwards?
You're slowing down.
I guess that makes sense.
The negative sign just means you're slowing down, or you're going, or you're coming. Yeah, negative velocity, negative acceleration. I see I did it again. I got my velocity mixed up with my acceleration. Slowing down would mean a negative acceleration. A negative velocity would mean you're turning around and going in the opposite direction. Yeah. Okay, so does somebody have a specific question from 26 through 39 you want me to do, or just kind of start?
Can you do 36?
36. Bowling ball moves with a constant velocity from an initial position of 1.6 meters to a final position of 7.8 meters in 3.1 seconds. What is the position time equation for the bowling ball? And then B, at what time is the bowling ball at a position of 8.6 meters? Okay, so what you're going to do is just plug into the formula. All right, so here is the position versus time formula. XF, final position equals initial position plus velocity times time. Okay, so we know we have an initial position at 1.6 meters. Okay. All right, so 7.8 meters is our final position. 1.6 meters is our initial position. We don't know our velocity. All we know is it's constant. And we have a time of 3.1 seconds. So if we plug all of that in, we can solve for the velocity and find out what our constant velocity is. So we're going to subtract 1.6 meters from both sides. Then we're going to divide. Okay, so 7.8 minus 1.6 is 6.2 meters, 3.1 seconds. There's our velocity. So divide both sides. So 6.2 divided by 3.1 is 2.0. I have to put the 0.0 because of significant figures. Got to have 2 in my answer. And that's meters per second. So that's my velocity. So A tells me what is the position time equation for the bowling ball. So the position time equation would be, I have to plug all of this in. Oops. So I'm going to go back up here and I'm going to say, all right, X final equals 1.6 meters plus 2.0 meters per second times whatever the time is. That is my position versus time equation for that particular problem. That if you start at 1.6 meters, you travel 2 meters per second for some amount of time, you will get to some distance xf. So this is the equation. So it's kind of weird because you had to use the equation to solve the equation for v to know to plug back into the equation. So that was A. And then B asked you to find the actual time. They wanted you to find what the time was if your position was 8.6 meters. Okay, so now we're going to erase all of this and plug in 8.6 for XF and solve the equation for time. All right, so 8.6 meters equals 1.6 meters plus 2 meters per second times t. And then you're going to solve for t. So how are we going to do that? Subtract 1.6, right? 6, not 8. So that's 7 meters. Make sure you're writing your units. 2.0 meters per second times t. So to find t, you're going to divide both sides by 2.0. Remember, your meters are going to cancel. That's going to leave you with just seconds. 7 divided by 2 is 3.5. Meters, because our seconds, seconds, because our meters cancel out. Okay. Okay. All right. Any questions on that one?
I just added the 1.6 and the 2, and then I divided by that. So I have
You added 1.6 and 2?
Yeah.
And what did you divide by? That gives you 3.6. 3.6 divided by 3.6 is 1.
No, I divided that by 8.
Oh, you divided 3.6 by 8.6?
I don't know.
I don't know either. But you see why you can't add the 2?
I think instead of dividing, I subtracted it. So I added the 1.6 and 2.
Okay, but you can't add them
Yeah.
because this is a multiply deal here. The 2 is a coefficient. It's not a term all to itself, like in math. So you can't add the 2 and the 1.6. You got to subtract you got to get the t by itself. So t is your variable. You got to get that by itself. And the way you do that is you subtract 1.6 from both sides.
Alright. Yeah, just added because there's just a plus sign there.
Yeah. If the 2 hadn't been multiplied by the t, then that would have been fine. But since it's 2t, you can't do that. That's like adding 1.6 and 2x. You can't add a 2x to just a plain number. It doesn't work that way. So remember, all the rules that you learned in algebra for how to solve equations and all of those kinds of things, all those rules apply here. It's the same exact thing. We just don't have x's and y's anymore. We have t for time, v for velocity, and we have units. But the units, m and s and all that, they're not variables. They're units. So they just get carried along with the number and they get canceled out like the number. Okay? So we treat units like numbers. They're not variables. Okay? All right. Anything else? Another question in 25 through 39? 39? 26 through 39?
Can you do like the 30 and 31? Can you explain this graph?
Mm-hmm. All right. Ooh. Okay, here we go. I'm going to give it a try. So on 30, a tennis player moves back and forth along the baseline while waiting for her opponent to serve, producing the position time graph shown in 2.11. I'm on page 57 of your textbook. So you can see that kind of zigzag line. So the first line is section A, it's going down, then section B is going up, and then section C is going back down again. Without performing a calculation, rank the segments of the graph A, B, and C in order of increasing average speed. Increasing average speed, meaning where is she going the slowest and where is she or he going the fastest? So what would we want to look for? If we're just using that graph, not using any calculations or anything like that, what do we want to look for in that graph? The slope. Whichever one has the greatest slope is going to mean the greatest speed. So which one is increasing or decreasing the most? Which one has the biggest slope? B. Okay, so B is our fastest one, so we want that one at the end. Which one has the smallest slope? C. So that's our slowest one. That one's going to be at the beginning. So C is the slowest, then A, then B. Okay? Yes.
Okay, so I do have a question about the fact, like, okay, so she's moving from like position, like place to place. And
So she's moving. Okay, so in A, maybe she's stepping back from the net. Let's say the net is our frame of reference. The net is our 0 point. If she's stepping back away from the net, that would be A. Maybe in B, she's going towards the net.
so the only
And then C, she's going back again.
that would be the sign, right? The slope would be the same.
Would-
One would be negative and one would be positive.
Exactly. So if you look at A is kind of, A looks like, A and C look like they have more of a negative slope, right? So that means maybe she's running away from the 0 point. If the 0 point is the net, she's running away from the net.
Okay.
In B, she's running up towards the net to hit.
I guess it was just she's covering the same amount of distance. So I was like, which one's faster? I don't know. But I
Goes by
guess
the
faster
slope.
is not the-
Yeah,
Not the word to use.
maybe not.
Okay.
They talk about their speed, but it would be the negative slope would indicate whether she's going back or front. Okay. So B says, 30B says, rank the three segments of the graph in order of increasing average velocity from the most negative to the most positive. Okay, so remember, speed has nothing to do with direction. So speed is just speed. Okay? So you look at the slope itself, which one has the fastest slope, the steepest slope versus the not steepest slope. That's a word. But in B, we want to look at the sign because that's saying average velocity. So we want to look at whether it's a negative slope or a positive slope. So which one, and then that's why it says from the most negative to the most positive. So which one of those, A, B, or C, is your most negative slope? A. Then your most positive slope would be what? B. So your order is going to go A, and then C, and then B. Does that make sense? Okay. So pay attention to the wording. If we talk about speed, we're just talking about the slope itself, steep or not steep. If you're talking about velocity, you're talking about is it a negative slope or is it a positive slope? Okay. Okay. Was that the one you were asking me about, Taylor? Not Taylor. You're Tyler. About taking the average velocity and all that? Yeah. So you didn't have to find the slope of each one of those. They just wanted you to look at the graph. And 31 looks like it's the same type of deal. 4 slopes, 4 different motions. Rank the motions in order of increasing speed and then increasing velocity. Okay? So, next question. 39, yes. Okay, here we go. If you were riding in a car on a straight stretch of 2-lane highway with a speed of 26 meters per second, at a certain time, which we will choose to be time 0, you notice a truck moving towards you in the other lane. The truck has a speed of 31 meters per second and is 420 meters away at time 0. This sounds like one of those bad word problems from 3rd grade that made you cry, doesn't it? Okay. Write the position time equation for motion for your car and for the truck in the other lane. And then B, plot the 2 equations on a position time graph. At what time do you and the truck pass one another going in opposite directions? Yeah, it is that terrible word problem. But at least now we know the position versus time equation. So we got x final equals x initial plus velocity times time. Okay. All right. So A, write the position time equation for the motion of your car and for the truck in the other lane. Well, let's do motion of your car first. All right, so our initial choose times 0. Your truck will be moving. All right. So we know our velocity is 26 meters per second. Certain time, which we choose to be t equals 0. So in the first part, they're just wanting the equation. They're not wanting you to solve the equation. Okay? So the equation is going to be our initial position at time 0 is 0. Okay? So our final position is just going to be equal to whatever my velocity is times whatever my time is. So this is the answer for A. 26 meters per second times t, whatever time is. Okay? That's for the car. That's for the car. Whoops. For the truck, okay, for the truck, we know that the truck is 420 meters away. So its initial position is 420 meters away from where you are. And we know that it is going how fast? 31 meters per second. Is it traveling in the same direction as you? No, so we got to put a negative sign right there because it's traveling towards you while you are going in the opposite direction. So here you are at time 0. You're going in this direction down the highway. The truck is coming in the other direction, but it's 420 meters away. So its velocity is negative 31.31 meters per second at time t, whatever that time is. So this is for the truck. This is for the car. Okay, does that make sense? Those two equations? Okay. This is where sketching out the problem can really help you understand what's going on. Because if you sketch out your little 2-lane highway, and I can't draw worth a lick, but here's car, so I'll just put a C, and that's time 0. Here's your truck right here. And that distance is 420 meters away. The truck is coming this way, you're going that way. So that's going to help you keep those negative signs and positive signs straight. Okay? All right, so then B says plot the two equations. To do that, you're just going to need to come up with just make you a data table of various times, plug them into the equation, and see what your final distances are. Okay, so you'll have an equation of time and XF. And you can set times of whatever you want, 0, 2, 1, 2, 3. Okay, and you'll do that for both equations, and then you will make a graph of both lines. And once you get that graph made, that will help you answer question C, because where the two lines cross is where they pass each other. Okay, so if this is, I have no idea. So let's say that's your car, and then this is the truck. Okay, where those two lines cross each other, that's where the car and truck pass. Okay, all right, so 1 through 25 should be much easier than the ones you did. You got the hard stuff already done. So 1 through 25.